So in this particular section, we're going to be talking about multiplying, dividing rational expressions. Remember, rational means we are dealing with a fraction. And expressions means there's no equal to sign. So if there's no equal to sign, we're not doing any solving whatsoever. Remember that. Here are our objectives for this particular section. So, rational expressions, as we've discussed, rational is fractions. Expressions means there's no equal to sign. They're written in the form of a fraction. One huge requirement is that you can never let your denominator be equal to 0. Because if your denominator is equal to 0, you basically blow up the fraction, and that doesn't do us any good. So here are some examples of rational expressions. This is clearly a fraction. It's got polynomials in it, but that's okay. We can handle it. So here are 3 expressions that gives you an idea of what we're going to be dealing with. I'll be back to this page. So in this first example, we're going to talk about the domain of a rational function. Now, one of the things to remember is domain refers to the input variable. What variable are we actually plugging numbers in for? If you take a look at number A, or I should say letter A, we are plugging in letters for x, or numbers in for x. So, and we are looking to see what numbers we're allowed to plug in for our x's in this particular rational expression. Now, here's the deal. Remember, do you see this as a denominator? We mentioned that our denominator cannot be equal to 0. So our denominator was x minus 6, which means it cannot be equal to 0. And we have given ourselves a little equation to solve if you take a look at this. And when you solve it, you see that x cannot be equal to 6. So x can be any real number we want except for 6, because if we allow that to be 6, then we blow up the fraction, and yeah, that's not a good thing, right? Okay, let's take a look at letter B. Again, we have this denominator, and we're not allowed to let it be equal to 0. So we have x squared minus 3x minus 10 cannot be equal to 0. Okay, so we've solved these before. We have a second degree equation, which means in order to solve it, we need a multiplication problem, right? This is clearly not a multiplication problem. So we need to change this subtraction problem into a multiplication problem. Remember how we do that? Hopefully you said factor. So you're right, we're going to have to factor, which means, just as a quick refresher, we take the first number, we multiply it by the last number, and we get negative 10. And I'm looking for all the numbers that multiply to negative 10. And I'm hoping one of them will add to a negative 3. So most of you are probably thinking 2 times 5. Well, 2 times 5 is definitely 10. But remember, we need a negative 10. And at the same time, we need it to add to a negative 3. So we have 2 possibilities. We either have a positive 2 and a negative 5, or we have a negative 2 and a positive 5. Which one do you guys want to choose? Right. So if you take this first one, it will definitely add to a negative 3, which means we are going to take out the negative 3, and in its place, we're going to put in the 2 numbers you just found. And when we pair them up, we see what's in common with the first pair. We see what's in common with the second pair and factor them out. And then we see that x plus 2 is in common and x minus 5 is in common, which means those can't be equal to 0. Solving this gives me x plus 2 not equal to 0, which means x cannot be equal to a negative 2. and x minus 5 can't be equal to 0, which means x cannot equal 5. And there it is. X cannot be equal to 5, and x cannot be equal to 2, just like we found. Okay, in this last one, letter C, the 4 is in the denominator. Now, here's my question to you. Is there an x in this denominator? Hopefully you said no. So, no x in here. Since there's no x, that means we're not plugging in a number for the denominator, are we? So that means the denominator will always be equal to what number? Right, 4. Then the denominator will always equal 4. And that's okay. That's okay. We can always let the denominator equal 4, which means we can use any number we want in this particular denominator. Cool? So far, so good? Okay. Now, let's move on to simplifying these rational expressions, these fractions. That means we're basically going to put it in lowest terms, simplest forms. Another word that we're going to look at for this is we are going to reduce them. Okay? So how do we do that? First, we have to factor the numerator and the denominator as well, completely. Once we do that, then we are going to divide out, or another word for divide out is we are going to cancel what's in common between the numerator and the denominator. Okay? So, let's take a look. Here is one rational expression, and they're asking us to simplify. And simplify means to reduce. So, that means we need a multiplication problem, because the only way to reduce is multiplication. And once again, I've got addition, I've got subtraction, they're not helping me out. So if you remember the very first step here, we need to completely factor the denominator and the numerator. So I'm going to let you do the work on factoring, and hopefully we'll agree on how it looks like when we factor it. I hope you got that. And since it's now multiplication, I can cancel something from the top and the bottom that's exactly the same. And you notice the x plus 4s are exactly the same, so we're canceling those out. And basically that gives this to be a 1, because x plus 4 divided by itself is 1, and divided by itself is 1, which means that is a 1 times what's left, which just gives us x minus 1 over x minus 5. Now, I have a question for you. Can we cancel these x's? Some of you may be thinking yes, some of you may be thinking no. Here's how I need you to understand this. Since they are attached by addition, well, in this case, just subtraction, I need you to think of addition and subtraction like super glue. These guys are super glued together, which means it's either all or nothing. I cancel x minus 1 with another x minus 1, or I cancel an x minus 5 with another x minus 5, which clearly we don't have. So these x's right here cannot be canceled, which means your final answer will remain as x minus 1 over x minus 5. Good? Okay, let's look at another one. Now, again, they want us to simplify, which means they would like us to reduce. Now, remember the first step said factor completely. So in order to factor, we need things in descending order. I'm noticing the numerator is not in descending order. So what should be written first, the 7 or the y? Hopefully you said the y, and the sign in front of the y is negative, and then when I write the 7 second, that's a positive 7. With me? Okay, so now, do you see anything in common? Yeah, I really don't either except for one. But one of the things that I do remember us talking about is if the lead coefficient is negative, I get to factor out a negative. So that means I'm factoring a negative something out. And in this case, all I get to factor out is a negative 1. And remember, when you do that, that's the same as you basically taking both of these and dividing by negative 1. And when you do that, you are going to be left with a positive line and a negative 7. So your numerator looks like this. The denominator is okay. It was already in descending order. I don't have to worry about anything there. And I'm noticing a y minus 7 on the top and bottom, which means we can cancel, and all we're left with is a negative 1. Good so far? Cool. Okay, let's take a look at this next example. So, notice that x plus 5 on top? Yeah, I don't see any kind of square or third power or anything like that, which means it's just going to stay x plus 5. What about that x squared minus 25? Yeah, that will factor. So I'm going to let you factor it, and hopefully you agree with my factoring. Now, do you notice there's an x plus 5 on the top and the bottom, isn't there? Remember, that's like saying x plus 5 goes into itself once and x plus 5 goes into itself once, which explains why there's still a 1 on the top. The answer is not x minus 5, the answer is 1 over x minus 5. So sometimes it's beneficial to say how many times it goes into itself, so you make sure and put these little 1s here, because occasionally we need to remember that there's a 1 left over, especially on this one in the numerator. Okay, so far so good? Loving it. Now, let's look at one more to simplify. Looks like both numerator and denominator, yeah? Okay, so let's talk about that numerator. We have 2x squared minus 5x minus 12, and we'd like to factor it. So, anything in common that we can divide out, anything we can reduce by. Okay, so I hear you guys saying no. So no reducing. And now that means we get to take the first number and multiply it by the last number, which gives us a negative 24. And now I'm looking for all the combinations that multiply to negative 24 and at the same time add to a negative 5. So let's look. Of course, we have a positive 1 and negative 24, a negative 1 and a positive 24, and as we keep going down the list, we're looking to see if any of these combinations adds to this negative 5. So I'm not seeing it yet. Oh, wait, maybe I spoke too soon. 3 plus negative 8. If I add those, what do I get? Yeah, 3 plus negative 8 is negative 5. I think we found our combination, didn't we? Okay, that tells me we're going to do some replacing now. So we have 2x squared plus 3x minus 8x minus 12. And again, we get to pair them up, right? Take out what's in common. In the first pair, there's only an x in common. In the second pair, there's a negative something. What is it? Yep, that's right, a negative 4. So when I do this dividing, I'm dividing out an x. I'm left with a 2x plus 3 on the first pair. In the second pair, we're dividing out a negative 4. And that leaves me with a positive 2x and a positive 3. And now I'm noticing the 2x plus 3 is in common, so I'm going to factor that out, which leaves me x minus 4. Cool? Loving it. Okay, so that took care of the numerator, but we still have the denominator to deal with. And in the denominator, we have 16 minus x squared. Now help me out. Is that in descending order? No. So the book writes it a little bit differently, does it a little bit differently. Here's always my recommendation to you guys. Please, I suggest always doing it this way. always put it in descending order first. That's important. Descending order first, which means I'll write negative x squared plus 16. I'm noticing the first term is negative, which means I'm going to take out a negative 1, and I'll be left with x squared minus 16. Agreed? Okay, which means now I need to finish factoring that, and you guys have factored this before. We have x squared minus, or I should say plus the 0x minus 16. Remember how we spoke about that in class? All right, I fix that little 2 right there. So what two numbers will multiply to negative 16 and add to the 0? Yes, x squared plus 4x and minus 4x minus the 16. If I look at the first pair, out comes an x. I look at the second pair, out comes a negative 4. So I have x that factors out. I'm left with x plus 4. Factor out the negative 4. This becomes positive x, positive 4, which gives me x plus 4 times x minus 4. But remember, in the very beginning, we took out this negative 1, which means it needs to come back in the final factored answer. So the numerator matches our work. Their denominator doesn't quite match our work. They did it a little bit differently, but if you notice on this next part, here's that negative 1, isn't it? Just like we had. There's our negative 1. X plus 4 and x minus 4. So, I notice things are in common. We're going to cancel things that are in common. Because basically that's a 1 and that's a 1. Which leaves me with 2x plus 3 over x plus 4 with this negative down here. Now, let me ask you something. Remember, do we ever want our denominator to be negative? Hopefully you said no, which means I can put the negative with either the numerator or I can put it out front. And in this case, we put it out front. Why? Because it's a lot easier to deal with it out in front. Cool? Okay, let's take a gander. Such a lovely problem to reduce. See this numerator? Those are perfect cubes, aren't they? Okay, let's see what you remember about factoring perfect cubes. Remember, they will always factor to 2 parentheses. The first parenthesis is the cubed root. The second one is the leftover, and it's also a trinomial. Cubed root means you need how many of a kind? Yep, 3. So if I notice, x to the third means I have 3 x's, don't I? 27 means I have 3 3's. Yes? If I take the cubed root of x to the third, that's going to be x, isn't it? Which means I've used one of these x's. How many are left over? That's right, 2 of them. All the x's are done. 27. What's the cubed root of 27? That's right, 3. That's why you had me write 3 3's down here. So I used one of the 3's. How many 3's are left over? That's right, 2 of them. So I've used all my 3's. Now, remember, this second parenthesis is a trinomial, which means there is one more term missing. And that's the term that's in the middle. And how do you get it? You take the 2 numbers in the cubed root, multiply them together, and that gives you the middle of 3x. How are we doing? So far, so good? Coming back to you? Okay. One last thing we have to put in are our signs. And I don't care if there's a plus in the beginning or minus. This little knocked out face is what I'm always dealing with. 2 additions and 1 subtraction. And since the first, or this term, this polynomial, has a plus sign in between, then I'm going to put a plus sign to start with, which makes our little guy a pirate. Arr. And I have 2 signs left, a positive and a negative. It's like, well, which one do I put next? Here's how you decide. This 27 is a positive 27 at the end. This is already a positive 3, which means this 3 squared also needs to be positive if I'm going to get a positive 27. Does that make sense? Which means I've already used the plus, and that means the minus sign goes here. Which means our numerator looks like this. X plus 3, there's the cubed root. X squared minus 3x plus 9. That plus 9 comes from us squaring the 3 squared. Notice the x plus 3s are in common, which gives me my final answer, and I'm sorry, our work kind of covered the final answer, but the final answer is the x squared minus 3x plus 9. How are we doing? So far, so good? This whole chapter is going to use all of your factoring skills, okay? And I know we're doing a lot of reducing, because here's another one to simplify, which means we're reducing. Okay, so take a look at the numerator. Anything you can do with it. That's right, there's a 3 in common, so we can take out a 3, can't we? Look at the denominator. It's already 4 terms, isn't it? So since it's already 4 terms, all I get to do is pair them up. Okay, what goes into the first pair? That's right, they both have an x squared in common. The second pair, I know I'm going to take out a positive, because the first term is positive. The positive what? That's right, 2. So let's take a look. There's a 3 from the numerator we said was in common, right? So out came the 3 because we said the 3 was in common. See the pair up like we did? Which means, look, on the denominator, see they took out an x squared like we did, and they took out a positive 2 like we did. Notice these x minus 3s are the same. And so when we complete the factoring, this is what we get. Those x squared plus 2's cancel, don't they? Sometimes it's better to leave the x squared polynomial alone to see if it factors or not, because sometimes it'll just cancel. In this case, it did, which means we're left with just 3 over x minus 3. Question, can I cancel these 3's? Yay, I heard you guys say no, because in the denominator, that 3 is super glued to the x, isn't it? Cool. How you guys doing? So far, so good? Okay, love it. Now, we are going to get into multiplying and dividing these polynomials. Here's the cool thing. Everything we just did in these last 7 examples of reducing, we're going to do the exact same thing when it comes to multiplying rational expressions. Okay, we're going to do the exact same thing. Now I've got 2 fractions that are getting multiplied. The denominators cannot be equal to 0, otherwise we blow up the fraction. Notice numerator to numerator, denominator to denominator, right? But notice the first step is exactly the same as the last one. Factor, completely factor the numerators and denominators. I multiply them together, and then I get to hopefully cancel, right? Okay. So there's our workspace for this example that we're going to work on. Notice the 2 fractions. We are multiplying them together, right? Which means we take the numerator times the numerator and the denominator times the denominator. Agreed? All right. So that means we actually have 4 factoring problems that we have to work on. The first numerator, the second numerator, the first denominator, the second denominator. So let's go take a look and see what we're going to do. So here's numerator number 1. We have 4x x plus 8. And the question is, can I factor that? You're right, they have something in common. So we're going to take out that 4, and we're going to be left with x plus 2. Now, does this x have a square? You're right, it doesn't, which means I'm leaving it alone. I'm not going to do any factoring with it. We're leaving it alone. Okay? And now look at denominator number 1, which was 7x squared minus 14x. And our question is the same. Do they have anything that it's in common that we can divide both of them by? Yes, they both have a 7 and they both have an x. And by the way, for those of you who are visual people, please make sure that you do this step. That means I'm dividing each one of these by a 7 and an x, because now you can see what's left over. What's left over is just an x on the first one and a minus 2 on the second one. If you're this visual, please make sure you do it. So, numerator 1 has been factored. Denominator 1 has been factored. Good. Now, let's go talk about numerator number 2. That was the 3x squared minus 5x minus 2. Okay. Is there anything I can divide out of all 3 terms, like we did on the first one or the second one? You're right, there's not. So that means we have to make this into 4 terms. So we're going to do our little side work. And we are going to multiply the 3 times the negative 2, which gives us negative 6. And I'm looking for a combination that adds to negative 5, aren't I? So let me just redo that because that yellow is just a little challenging to see. So we are going to take 3 times the negative 2 gives you negative 6. I start with 1 times negative 6, don't I? Oh, wait. I think I found my combination right away. This will add to a negative 5. Yay! So, replace. I am going to take 3x squared, and instead of writing minus 5x, I am going to rewrite with the positive 1x and the minus 6x for that minus 5, and then minus the 2 at the end. And again, pair them up. Okay? Pair them up. First 2, last 2. First pair has an x. The second pair, because that first term is negative, I'm taking out a negative. And it looks like the number is negative 2 that I'm taking out. Okay. Out comes the x. What remains is a 3x and a positive 1. Take out the negative 2. What remains is a positive 3x. And negative 2 divided by negative 2 is a positive 1. And there are those parentheses that we so look forward to having, because when they are there, we can complete the factoring and make it a multiplication problem. So here is numerator number 2. How you guys doing? You with me on this? Is this making sense? This whole section is going to get you practicing your factoring. And last but not least, denominator number 2. That was the 9x squared minus 1. Is there anything in common like we had on numbers 1, denominator 1 and denominator 2? Yeah, there's nothing. But I still need to make 4 terms. But I'm missing even the middle term because I don't know what it's supposed to add up to. So remember, when it's missing that middle, you add the 0x in the middle. Okay, so here we go. Same thing, right? Time to do 9 times negative 1, which equals negative 9. I think this one's pretty easy. A 3 and a 3, right? That'll give me 9. But because it's a negative 9, one of these numbers has to be negative, doesn't it? And a positive 3 and a negative 3 adds to 0 in the middle, doesn't it? Okay, so we found it. So now, see if you follow along with what I'm doing. All right. I'm pairing them up. I notice there's a 3 and an x on the first one, and just a negative, but only a negative 1 on that second one. So, take out the negative 1. Looks like that becomes positive, and the negative 1 divided by negative 1 is also positive, which gives me 3x plus 1 and a 3x minus 1. Okay. And there is denominator number 2. So, back to the problem. And there's the factoring, just like we had. And if you notice, there's some things, we multiplied the two fractions together, so now it's one big fraction. Some of you are like, do I have to do that? No, but some of you should do this, and you know who you are. I multiplied the first numerator by the second numerator, which is why I have all this in the top. And the same with these denominators, which is why the denominator is quite large. I notice there are things in common, so I'm going to cancel them. I'm hoping there's something else in common. Oh, yay, there's more in common, so they get canceled too. And after all is said and done, this is what I have left, and there's no more canceling to be done. How's that? You guys good? Cool. Okay, let's talk dividing. Now, you guys know how to divide fractions. Here's a division problem, but it doesn't stay division. It turns to multiplication, and if you take a look, fraction number 2 flipped over, and then I get to multiply them together. But again, your denominators are not allowed to be 0. And you actually had 3 denominators. You had a Q, you had the S in the original, but when you flipped it over, R became in the denominator, which means there's 3 of them that can't be 0. And in order to divide, you basically make it a multiplication problem, and then you do what's normal. You simplify if you can. You do just like this last problem. So, let's take a gander. Let's see what this looks like. Here's our first problem. Okay, it's division, yes? Does division stay division on fractions? Correct, absolutely not. It turns to what operation? That's right, it turns to multiplication, and which fraction does the flipping? Yep, fraction number 2's got to flip, so here you are. It turned from division to multiplication, and fraction number 2 did a flip on us. How we doing? Good? Okay, so I'm going to let you guys factor this one, and hopefully your factoring agrees with this. There are things in common, gratefully. And that's about all we can cancel, and there it is. Does this make sense? Cool. Okay, so example number 12. Let's take a look. Wow, that's a fun looking problem, isn't it? So, here we go. We clearly have to make it a multiplication problem, which is the very first step you should always do when you have a division problem. Make it into multiplication. And once it's made into multiplication, you're going to have to factor. So let's work on that factoring a little bit to make sure everybody's on the same page. I am hoping that you will be able to follow. I don't want denominator, I want the numerator first. I am hoping that you are going to be able to follow along with me and how I'm factoring this. I don't see anything in common, but I want 4 terms. So I have to do 8 times 3, which is 24. I'm going to find all my combinations for 24. The numbers are either both positive or they're both negative. Oh, wait, I think I found it. I want a positive 14, and this adds to a positive 14. All right, so we found it. Quickly, as a matter of fact. That's why I always suggest stay in order. 1 times whatever, 2 times whatever, 3 times whatever, okay? So I still have the 8z squared, but instead of that 14, I'm going to put in the positive 2z and the positive 12z, and that will end with a positive 3. I'm looking for pairing these up and seeing what they have in common. This is what I'm seeing on the first pair. This is what I'm seeing on the second pair. Hopefully you're in agreement with me. So I have a 4z left and a 1. And on that second pair, when I take out the positive 3, I have a 4z and again a plus 1. And gratefully, those parentheses are matching up. I'm not going to force them to match up. I'm hoping they match up. So here is numerator number 1. That makes sense? Okay. Let's look at that other numerator. After we flipped it, this polynomial ended up in the numerator. So, nothing in common. I don't see anything that we can reduce it by. I'm going to then take the 35 and times it by negative 2, which is a negative 70. All right, here we go. Combinations for negative 70. 1 times negative 70, negative 1, positive 70. 2 times negative 35, negative 2, positive 35. 3 doesn't go into 70, 4 doesn't go into 70, 5 goes into 70. 5 and a negative 14, or it's a negative 5 and a positive 14. 6 doesn't go, 7 goes. 7 times negative 10, negative 7 times positive 10, and oh wait, I want a positive 3z, right? Looks like this combination multiplies to a positive 3. Okay, so now that I found my combination, it's time to replace. There's the 35z squared. There is the minus 7z, the positive 10z, and we finish it off with the negative 2. And we're going to want to pair them up like we have been doing. Factoring has the same routine. The same routine. Always, always, always. The same routine. Which is good for us because that means I don't have to memorize anything new for every problem. The routine, the pattern is the same. Hopefully you're following along as I've been talking with what I'm doing here on the screen. That parenthesis is in common. Yay for that, because if it's not, oh, that means we're up a creek. We may have done something incorrectly. Or maybe it just doesn't factor. And there is the numerator number 2. So if I go back, we factored this numerator and we factored this numerator. We didn't factor the denominators. I'm going to leave that up to you. But notice this is what we got. And we're noticing there are things in common. And we are canceling out what's in common. Wow, a lot of stuff canceled. Yay! We always want all that stuff to cancel. And there it is. Does that make sense? Cool. All right. Let's take a look at the next problems. Notice this one's multiplication, so that's already good. But this one is division, not so good. So we're going to have to flip that guy over, aren't we? Which we did. He has to flip. We flipped him. we're going to have to factor. So I'm going to let you do the factoring on this one. Here's something I'd like to point out. This was x plus 3 squared. That squared meant there was 2 of those parentheses. Do you notice they wrote the 2 parentheses out? It's very smart to do that. Very smart to write it out twice. Because that way you can see what is going to cancel. See, notice how both x plus 3's canceled out? That's why it's important to write it out twice. And there's that canceling. Oh, wait a minute. Wait a minute. Aha! The operation between the 5 and the x was multiplication. Since it was multiplication, we could cancel. And that's important. That means we could cancel. And that's what I am finally left with. How's it going? Cool? All right. So we basically be doing the same thing in this whole section. One last thing. Let's look at some stories, shall I say. Now, they tell me a company's cost per book for printing X particular books is given by that rational function. One of the key things that you have to understand is you need to know what the X stands for, right? Well, they tell you X is for printing X particular books. So X represents books, doesn't it? And they want to know what is the cost for 100 books. So what do you think you're going to do with 100? Yes, plug it in. Instead of saying C of X, notice that instead of saying C of X, they now say C of 100 because X got replaced with 100, which means the cost of 100 books. That's what this C of 100 means. It means the cost of 100 books. And after you plug it in and do all your work, you get 50.8, which means the cost is $50.80 for the 100 books. Good? Okay. There is a part B. Now I got 1,000 books. Do you think it's going to be any different? Correct. It's not. Plug in the 1,000. So now this notation is the cost for 1,000 books. That's what that means now. The cost for 1,000 books. And after all is said and done, the cost per book for printing 1,000 books is $5.80, which makes sense. The more you print, the less expensive it is. So hopefully that helped you out. Hopefully that made sense to you. Look forward to the next videos. Have fun!